I'm going to talk today about performing one-dimensional quantum simulation using a solid-state platform. And the motivation for this talk is really to develop the building blocks and the tools necessary to use a solid-state system to perform quantum simulation. So this work is motivated by the extensive amount of work that's been done in the field of cold atoms towards quantum simulation. So here, magnetic and optical traps are used to create a lattice of sites and then trap and control a large number of atoms at specific sites. And these external fields can then be used to control the interactions of the atoms, allowing for the creation of correlated systems and the ability to realize a wide range of many-body Hamiltonians. And so with this method, they do really have a very well understood system where they know precisely what the Hamiltonian of the system is. They're able to control it very precisely. It is, however, difficult for them to reach temperatures, low effective temperatures where correlated ground states occur. And they are inherently, as particles are continually evaporating from the lattice, they're inherently measuring non-equilibrium phenomena. And so with these cold atoms, what they're doing is simulating systems which appear in solid-state physics. So what if instead we use a solid-state platform to simulate this solid-state physics, which it could naturally support the physics we wish to study, for example, superconductivity, and then to use that to do quantum simulation. So there are a few examples. Really exciting work has been done creating artificial graphene by patterning gallium arsenide and by depositing carbon monoxide molecules on copper in these lattices. And so these have been very successful. But there are still some challenges in terms of being able to create a reconfigurable platform that has nanoscale control, which also includes strong sign-tunable electron-electron interactions, which are very important. And we want to be able to engineer devices on the single electron level and then simulate a wide range of many-body Hamiltonians, for example, the Hubbard model and high-temperature superconductivity, which could give insight into high-temperature superconductivity. We have been exploring a new platform, which is the oxide heterostructure lanthanum aluminate strontium titanate. And so it's a very exciting material. These are both insulating oxide materials, but when a thin layer of lanthanum aluminate is grown on top of the strontium titanate, there's a high mobility two-dimensional electron liquid that forms at the interface between these two materials. And it's a very rich interface. It exhibits a tunable metal to insulator transition, electrically tunable superconductivity, and spin-orbit coupling, and then even electrically tunable magnetism. So it really is a very rich system which exhibits nearly every phenomena in the solid state and makes it a very interesting candidate for a solid-state quantum simulation platform. So one additional ingredient that we need then is the ability to control all these properties on the nanoscale. And to do that, we've developed a conductive atomic force microscope lithography technique. And so again, we have strontium titanate and then a thin layer of lanthanum aluminate grown on top. It's usually around 1.2 nanometers. So in this case, the interface is naturally insulating. But we can deposit electrodes which can contact the interface and then use a conductive atomic force microscope tip, which when positively biased will deposit protons on the surface of the material, which then induces a conductivity at the interface. And these wires or these structures can be as small as 2 or even 1.5 nanometers. And so with this technique, we can also then erase by applying a negative voltage to the tip, which would allow us to selectively erase the structures and create barriers or constrictions. And so with this technique, we can do a variety of things, such as create single electron transistors at the interface. And this single electron transistor is essentially a solid state atom. It's a 1.5 nanometer conducting island, which is then precisely controlled. And so if we want to build quantum materials, we need to start with an atom. These devices also exhibit electron pairing without superconductivity, which indicates strongly attractive electron-electron interactions. We're able to create quantum point contacts where a constriction in the wire acts as a quantum point contact and allows us to see conductance in the wire, which increases in steps of E squared over H, indicating that we're able to control the number of quantum channels in the wire by tuning a gate voltage. And then finally, we also see that we have tunable electron-electron interactions in these devices. So using a gate, we can see a transition from pair tunneling, which indicates an attractive reaction, to single electron tunneling, indicating a repulsive reaction. So with this AFM lithography technique, we really do have the ingredients that we need to perform quantum simulation. We have these strong controllable electron-electron interactions, and it's reconfigurable on the nanoscale. So again, we're going to use this nanoscale control, and we do have, the interface has a typical density of 10 to the 13 per centimeter squared. This corresponds to about 1 electron every 3 nanometers. So we truly do have control over the interface on the scale, where we can have 1 electron per feature. And so this would allow us to create a lattice of sites for putting electrons, which doesn't have to bear any resemblance to the underlying lattice of the material. And in this way, we could create any number of one-dimensional or two-dimensional lattices and simulate a wide range of Hamiltonians. So again, we have this unperturbed conducting interface, which is also superconducting, and then we can perturb from this by adding structure to it and perhaps undergo quantum phase transitions into new states. And so here we have Feynman, who first pioneered the idea of quantum simulation, thinking about all these states that we can create with this technique. And so this is the ultimate goal, and we've decided to first focus on the one-dimensional case because it's more theoretically tractable. So let me now describe the devices that we've been creating. These are one-dimensional superlattice devices. And again, we're applying a positive bias to an AFM, to atomic force microscope tip, to create a conductive path at the interface of this material. And here we're just creating leads so that we can do 4-terminal measurements. And then the actual device itself is created by applying a series of negative voltage pulses to the AFM tip. And this will create a series of barriers in the wire. And then this is in series with a quantum point contact, which is just a restriction that should allow us to tune the number of channels, the number of quantum channels in the device. So here, by applying these negative voltage pulses, we've created a one-dimensional lattice of conducting sites in this wire. So the devices I'm going to describe today have 5 nanometer lattice spacing, and they consist typically of 18 lattice sites. And these are in series with a quantum point contact, which is just indicated by those 2 lines there. And again, these devices are written at room temperature and then cooled down to millikelvin temperatures in a dilution refrigerator, where we can perform magnetotransport measurements as a function of an out-of-plane magnetic field up to 16 Tesla, and then also as a function of a local gate voltage that we apply to this gate, which is also written using the same lithography technique. So here, let me first show you data from a control device. So this is just a single quantum point contact in a wire. And so if we look at these conductance curves here as a function of this gate voltage, we see that the conductance increases in steps of 2 E squared over H. And then this here is a transconductance plot, so a derivative of these curves with respect to side gate voltage. And then we can really see how the plateaus evolve. So these blue regions here, where the derivative is 0, indicate the plateaus. And we can see how these evolve with magnetic field on the x-axis and then this gate voltage on the y-axis here. So now then we can add the superlattice in series with the quantum point contact device. So again, we have the conductance curves, increasing magnetic field from left to right, and then sweeping the side gate voltage. And so while we do see some signatures of quantized conductance here, the superlattice, and then when we look at, it's much more apparent here in the transconductance plot. So the the magnetotransport revealed through this transconductance, which can be interpreted as a local density of states, exhibits a complex manifold of states which is not present in the control device when we introduce this superlattice. And so currently we're continuing to study how changing the parameters of the superlattice, spacing of the sites, depth of the barriers, the number of sites can change these features that we see. And so we have studied several 5 nanometer superlattice devices. And the devices show similar features, but they're not identical. So there are definitely some things we need to work out experimentally to make this process fully repeatable. We've also begun to do some theoretical modeling, starting with modeling a simple nanowire in this material. And so hopefully we can use the results from these experiments to constrain and parameterize these models to better understand the system and help us really develop these building blocks to for this quantum simulation platform. So again, our goal is to do quantum simulation with this solid state material. And we have, so the material is lanthanum aluminate grown on strontium titanate. It has these electrically tunable properties as well as nanoscale control over the interface. And we've performed preliminary experiments with these one-dimensional superlattice devices.